Continuing on with Chapter 3 for evaluating the properties. As I've stated before, any two independent property will allow you to look up or determine all other intensive properties. This is a critically important item that we will take advantage of time and time again throughout the rest of the course for trying to figure out what is our conservation of energy. Temperature, specific volume, and pressure and specific volume are frequently used as two independent properties simply because they remain independent throughout the entire spectrum of the substance. And as I already stated earlier, when you are at the phase change temperature, pressure and temperature are not independent. When they are superheated or subcooled, they are independent. But as they are changing phase from liquid to vapor, they are not independent. Let's consider a closed system of water initially at 20 degrees C. That is represented by this schematic here. First of all, I've got a piston on here with a certain, shall we say, weight. If the liquid expands or contracts, that weight will move up or down such that it is always under the same pressure. Therefore, this type of schematic shows that we are at a constant pressure. Please be sure that you understand that. And now we are beginning at 20 degrees C here at this blue dot location with this as a specific volume. Let's first look at our temperature versus specific volume graph for water. Each of these lines that are on this graph are constant pressure. This line here that I'm traveling along is atmospheric pressure, 1.014 bar. Here I have a 10 megapascal pressure, and that follows in this same type fashion. It's important to realize that everything underneath this dome is a two-phase type material. It is part liquid, part vapor. Everything out here is vapor, and everything over here is compressed liquid. So here we had begun at 20 degrees, and then we will go ahead and heat it until we are at 100 degrees, where we will change the phase from being pure liquid, going all the way over to 50% liquid, 50% gas, and then finally 100% vapor. Once you are at 100% vapor, then the temperature can continue to increase as you add more heat or energy. It is critical that you understand this figure. We can replace temperature with pressure and it will look similar. We can replace specific volume with enthalpy or entropy, and again, it will look similar. You will have a dome, and that dome will be where your fluid is changing from liquid to vapor. All right, so what have we done? I've gone from, this dot here at state 1 up to this blue dot at state 2. And what we have done is we've added heat. So we have added heat into the system, and adding that heat into the system, it has expanded. So this piston has risen, but it's only risen a small amount, such that the specific volume changed from where you were at state 1 to where you are at state F. But at this state F, this is where you are 100% liquid, but you are at the boiling temperature. As you continue to add more heat into this system, the volume has increased. and therefore we are now at this location here. So our specific volume, having gone from state F, we are over here, and you can see that we are approximately 50% liquid and 50% vapor. Any time that you are under the dome, you will be having a two-phase liquid-vapor mixture. And once again, this line here is a constant pressure, but you can see that at 100 degrees at atmospheric pressure, you can be pure water, 50% water and vapor, or 100% vapor. The pressure is constant, and that's why temperature and pressure are not independent when you are in the two-phase region, because our specific volume is changing quite a bit between our liquid at atmospheric pressure 100 degrees C and our vapor at atmospheric pressure 100 degrees C. How do you calculate out what the quality is? The quality is almost universally identified with the variable x, and you can calculate it in several ways. One way is it is the mass of the vapor relative to the total mass, which would be the mass of the liquid plus the mass of the vapor. The quality only has significance within this domed area, and the minimum value of quality is 0 when you are on the line of pure liquid about to change phase, going to unity, 100% gas or vapor, when you are on the the right side of this bell-shaped type curve. Once you have added enough heat such that you are at this location, for atmospheric pressure, you are now at 100% vapor. Any additional heat that you add into this system will now, still being at a constant pressure due to this schematic, the temperature value will increase. And that's demonstrated here, that we have this location for our specific volume, which has increased, but also our temperature has increased. Everything over here to the right of your phase change envelope is considered superheated vapor. You will need to be able to use the steam tables, or for that matter, the air tables, the refrigerant tables. But the two fluids that we use most frequently are the ones that are abundantly available to us: water and air. Table A4 lists all the superheated values. Table A5 we use very infrequently, and that is the compressed liquid. Tables 2 and 3 are what's happening while you are at the phase change temperature for that given pressure. Many of your homework problems will address this exact need and usage of the steam tables.